Okay, folks, in the last video, we ended up with examples. In this video, I told you we're doing more examples on top of what we've already done. But with the exception of the first one, we're going to flip the script and we're going to go back and we're going to look at names and draw structures from the names. So that way, we'll just have some practice going the other way. All right, so let's take a look at this molecule first before we get there. CH3, CH. And off of this carbon, let's put an OH group, all right? And then CH2 and CH2 and a carbon with a double bond O and a CH2 and a CH3. And we are expected to provide an IUPAC for this molecule, at least an IUPAC. All right, so how do we do that? Okay, so here's the story, folks. It's the same as always before. Here we see a carbon double bond O, and that carbon double bond O, guess what? It's a ketone. And then we see an OH group up here, and that OH group is a alcohol group. So we have a ketone, and we have an alcohol. And if I go back to this chart, and I look at this chart, I'm going to see ketone right above the alcohol. So what that means is that I'm going to name it as a ketone, and that means I will end it in O-N-E. And then to name the alcohol group, folks, I need to name it as a substituent. So I'm not going to use O-else. I'm going to name that as a hydroxy. Again, it's a substituent. It is a piece hanging off of the main chain. And in order to name that the proper way, we use the word hydroxy in order to do it. All right, so I now know I need to use hydroxy, and I also need to use -one as the ending. All right, so longest carbon chain, that includes the ketone. Okay, I forget about alcohol. Alcohol's trash. Alcohol doesn't mean anything right now. All right, so longest carbon chain, 1, 2, 3, 4, 5, 6, 7. There you go. Goodness gracious. Why couldn't I give you something else other than 7? That's just the way it worked. All right, so 1, 2, 3, 4, 5, 6, 7. And this is a heptane. Drop the E and add O-N-E for own. Now, I'm going to number closest to the ketone. Again, forget about everything else. It's all trash. Ketone is up front, your best customer. And because of that, you give it priority over everything else. Okay, so with that said, how do we number? Well, if we start from the left, it's going to give the ketone 1 and a 2 and a 3 and a 4 and a 5. And of course, if we start from the right-hand side, we can do a 1 and a 2 and a 3. So 3-heptanone is going to be the beginnings of the name that I'm writing down. All right, now what we have, everything else is taken care of, right? The ketone's now named, the carbons are now named, except for the OH group at the very end. Now, because I have numbered from the right, I have to continue on with it in that direction. So this is carbon 4, that is carbon 5, this is carbon 6, and there is carbon 7. So at carbon number 6, I have an OH group. That is a substituent, not the main chain. That's not the main functional group. And in order to name it, I have to use the word hydroxy. So at carbon number 6, I have a hydroxy unit. And the name of this is 6-hydroxy-3-heptanone. Folks, there you go. Is this a common name? And the answer is no, not really. And the reason it's not a common name is how on earth would you give me a common name for this piece that has that OH group at that position? That would be a very difficult chore to do, at least for now. All right, so 6-hydroxy-3-heptanone. I would only ask for IUPAC during this time, and that is it. All right, so now let's take a look at these examples. These, they flip. They give me the name, and they want me to draw the structure. It's not a problem. Not a problem at all. We can do these. If we can go one direction, we can go the other direction. So if I take a look at the first one, it's diisopentyl ketone. That's what they want me to draw. Okay, let me show you how easy these are. My ketone group is a C double bond O. There you go. Isopentyl means 1, 2, 3, 4, 5. Pentyl, 5 carbons. However, this is an iso group. So that means I need to take one of those carbons and I need to do beep that number to it. So there's the iso unit, right? And there's 5 carbons in total. 1, 2, 3, 4, 5. They're just not in a main long continuous chain. All right. So if there's one isopropyl, then I'm going to have to do the other side the same way. And there you go. There is diisopropyl ketone. All right. So there's example number 1. Example number 2, 3-methyl cyclohexanone. All right. Well, this is just as easy. Cyclohex is a 6-membered ring. There it is. And let me redo that end because it almost looked like 2 methyl groups were hanging off. So there's my cyclohexane. And one means a ketone. I'll put it anywhere I want to put it. So there's spot number 1. It will always be spot number 1 no matter where I start it. And then at the 3rd carbon, I have a methyl group that is hanging off. All right, so this is the 1st carbon. I can go left or right. It doesn't matter. I'll go right. So this is the 2nd carbon, and this is the 3rd carbon. So on the 3rd carbon, there we go. There it is. There's my methyl group. Okay, so next, 2,4-pentane-dione. All right, so if I go up here to the top right-hand side, pentane, 1, 2, 3, 4, 5. Dione means 2 ketone groups. Where are they? Well, they're at carbon 2 and carbon 4. So at carbon number 2, I have an one, and at carbon number 4, I have an one. So there's 2,4-pentane-dione. There's 3-methyl cyclohexanone, and down here at the bottom is diisopentyl ketone. So we've got one more. And this one more is 4-bromo-3-heptanone. It seems like I love heptanones. Well, that's just the way they worked out. 1, 2, 3, 4, 5, 6, and 7. And then on carbon number 3, I have an one group. So on carbon 3, I have a double bond O. It is a ketone. And at carbon number 4, I have a bromo group. Once again, it doesn't really matter if I draw it up or if I draw it down. I chose to draw it down because my bromo and the oxygen would look really close together on a sheet of paper. And they are really close together in the molecule as well, and they would want to be as far apart as possible. So those bonds freely rotate, and because they freely rotate, that carbon can twist and turn in order to get bromo further away from the oxygen of the ketone group. So there's 4-bromo-3-heptanone. Folks, that really is all there is to nomenclature. I think that if you have made it through Organic 1, and if you've made it through this part of Organic 2, I think the nomenclature might be getting a little bit better for you, or at least I hope it is, all right? This is no more difficult than anything else that we have ever done. All right, so with that said, that wraps up the nomenclature portion of the lecture, and now we need to take a look at reactions. All right. Oh, no! I know what you're saying. It's reactions. But we just really have ketones and aldehydes to deal with this time, with a few extra little sprinkles of major reactions that have been discovered by people that are kind of special, which is why we named them after their founders. All right, so let's take a look at reactions. I'm going to give you an intro about what all of these reactions do, because that's why they're called type 2. Type 2 carbonyls undergo a very similar reaction scheme as far as mechanism goes. All right, so with type 2, that's the key. We're no longer in type 1 that we've studied in the previous module. Type 2 always has a carbon to the left. It always does. And then here we have a carbon, or in parentheses, I'm going to put a hydrogen. It could be either or, because really we're only focused on aldehydes and ketones here. So a ketone is between two carbons, and an aldehyde is a hydrogen on one side instead of a carbon. So this is what we have. This is our aldehyde version or our ketone version. So in the previous lecture module, we introduced a nucleophile. A nucleophile was something that carried a negative charge. A nucleophile wants to be neutral. It's neutral loving. Nucleophile. Don't remind me of the pedophiles. All right, so nucleophile comes in, loves to be neutral, and it sees this little bitty molecule that it can take advantage of. All right, so the nucleophile, like before, guess what? It does the same thing. This oxygen is electronegative. This oxygen wants and wants and wants and wants and wants electrons, just like it did before. So it's an electron sucker. So the nucleophile is going to come in and it's going to look at this carbon that's in this relationship that's not very good for carbon because it's just getting sucked of all the money that it makes every day. And that oxygen just takes and takes and takes. And because of that, this carbon becomes partial positive and the oxygen becomes partially negative. So this is the very first step of the mechanism that begins to go on. The nucleophile goes in, sees this carbon that's in this nasty, awful relationship and says, I can make it better for you. Just give me a chance. And the carbon says, okay. And then the oxygen sucks the remaining electrons away and pop, off it goes. So what we end up with temporarily is a carbon that has now broken the double bond. And this oxygen carries a free set of electrons now. Well, a nucleophile has came onto here, and we still have this carbon or a hydrogen, depending on if it's a ketone or an aldehyde, over on the right-hand side. There's no difference here, right? So just like with the very first step, with type 1, this is the same step for type 2. Now, this is where things begin to change. Because this oxygen, now that it has a negative piece. And this oxygen in type 1 says, oh no, I made a mistake. You need to give these electrons back so I can make this double bond. Here, oxygen, take them, take them, take them. And the oxygen says, okay. And then it's got to get rid of a group. And we typically had a leaving group, pop, off it went. And if we were lucky, the nucleophile stayed. And what was there prior was released. And we called that the substitution part of the reaction. All right, well, this is where type 2 begins to take a turn. Type 2, oxygen does the same thing. Oxygen goes in and says, oh no, oxygen, I made a mistake. And then it kind of shoves the electrons back to carbon. And carbon looks at these two groups now. And it looks at this nucleophile group. And it looks at this carbon and this hydrogen group. And it says, I really don't want to get rid of any of them. Sorry. You're the one who started all this mess anyway, oxygen. You're the one who said you wanted all of these electrons, and I gave them to you. And that allowed me to kind of partner up with this new nucleophile that came in, and I'm perfectly happy. I mean, I have 4 bonds. I'm neutral. I've got 3 other people that like to love me better than what you did. So I'm in a perfectly good spot. Sorry, you got to fix yourself. And oxygen says, oh no, what am I going to do? I've got all these electrons. I've got this negative charge. I've got to push these electrons somewhere. I can't hold this negative charge. I've got to do something with it. Well, that is where this mechanism takes a turn. And this is the type 2 part of the mechanism that's going to be a little bit more important. All right? So this is where type 1 and type 2 have a difference. Type 1 substitutes. That substitution allows the nucleophile to come in, and carbon kicks off what was there. In type 2, it does not do that. When aldehydes and ketones react, the aldehydes and ketones look at the groups and says, you know, I'm going to keep them. I'm not going to get rid of anything. I like this nucleophile that came in. This nucleophile makes me feel good. This nucleophile gives me compliments. This nucleophile, it might be the beginnings of dating. Who knows? We're always a kind of a different person in the beginning, all sweet and innocent until they know the real true colors. All right, so this carbon right now is kind of going goo goo gaga over the nucleophile that came in. And it doesn't want to lose it. And then the problem is this piece that was on here, this piece is a carbon or a hydrogen. And these we've never really gotten rid of. I mean, those carbons, if they are connected to another carbon, these particular things are not very good leaving groups, right? The electronegativities are the same. There is no drama. There is no electron pull. I mean, these carbons kind of have a utopia going on. And why do they want to screw that up? So the left-handed carbon and the right-handed carbon here, those electronegativities are no different. They get along perfectly fine. There's no drama. There's no cursing. There's no throwing stuff at each other. I mean, this is a perfectly good relationship. Hydrogen is the same way. If you take a look at the electronegativities of either the carbon or the hydrogen, they're going to be pretty close. I think it's like 2.4 and 2.1 if I'm not mistaken. So these, because they're close, there's no drama, there's no issues, there's no electron pulling, there's no electron pushing. Carbon's not going to get rid of them. In the top one, that's where it was different, because we had this carbon double bonded O to like an oxygen of a carboxylic acid or an oxygen of an ester, or we had some type of group that was a very good leaving group here. The reason it was a leaving group is because it had an electron or electronegative atom that was associated with those functional groups, so it could pull those electrons away, go off on its own, and be perfectly happy. But here, we do not have that scenario. All right, so both ketones and aldehydes have a carbonyl. Both ketones and aldehydes undergo type 2 mechanism. Both ketones and aldehydes break the double bond in the beginning, and then that double bond tries to reform, and the ketone and the aldehyde says, no. That's the magic word. No, oxygen, you're not going to get it. I'm sorry. You messed it up. You made all of this thing happen before, and now you're just going to have to suffer with the consequences. It's like a punishment. That's what it is. I mean, if you've got kids, I hope that you are disciplining your kids, and that if they make a bad decision, they live with that bad decision because you've tried to tell them otherwise, right? That's what carbon's trying to do here. It tried to tell carbon, don't go and take the car and stay out in the middle of the night and then come back a little bit later thinking that I'm not going to do anything. I now need the car keys. You're not getting the car back. You're not getting the double bond back. That's what all of this is all about. All right. Now, before we go through, I at least want to talk about stability, and I want to talk about the differences between the ketone and the aldehyde at least. So if we take a look at the two choices here, we have a ketone, which is a carbon double bond, at least sandwiched between two carbons. And we also have an aldehyde, and the aldehyde is sandwiched between a carbon and a hydrogen. The question is, which one is more reactive? Okay, now they both undergo reactions. Okay, they both undergo reactions. But out of the two choices, we're going to have the tendency of one reacting a little bit better than the other. And the answer here is aldehydes are going to be more reactive. Right? And the question is, why? Well, okay, first off, they both have a carbonyl. They both have a carbonyl, which means they both have the same electronegative oxygen on them. And that electronegative oxygen is an electron puller, and they both get pulled of electrons as far as the carbonyl carbon goes. All right, so if that's the case, aldehydes have a hydrogen, ketones have two alkyl groups, and out of the two choices, carbon puts up more of a fight. That carbon has a higher electronegativity than the hydrogen does. So if we're getting into a three-way fight, and oxygen pulls and pulls and pulls, and these electrons get pulled up, well, the carbon here is going to kind of fight back on that a little bit. It's got more muscle, and it can put up a larger fight when it concerns the oxygen's electron pulling as far as the molecule goes. Now, hydrogen, on the other hand, hydrogen's a little bit weaker. Hydrogen's electronegativity is a little bit lower. Because of that, it can't fight as hard, or it can't throw as hard of a punch if they do get into a fight or an argument. And oxygen has its way over the hydrogen a little bit more, meaning that the oxygen here can pull the electrons away. This carbon becomes uncomfortable. Hydrogen can't put up a fight or play the tug of war game as well, and we start to see a loss of connectivity there. And because of that, the aldehyde is a little bit more reactive because it's more prone to those reactions. That carbon is going to basically be more positive. That's how I want you to think of that. The carbonyl carbon is a little bit more positive than a carbonyl carbon of a ketone, all right? Another reason that these two things have difference in reactivities is that the aldehyde is more exposed. If you take a look at the carbon in the ketone group, it is surrounded by these carbon pieces, and sometimes they're nestled in the middle of a molecule, and they're somewhat hidden or they're tucked away. So imagine you going naked on the beach, and you walk out and you are surrounded by friends. I think that you would feel more comfortable going out onto the beach naked, surrounded by your friends who are kind of covering you up. Well, the same thing, not quite though, happens with an aldehyde. They are walking out naked on the beach. They are exposed. However, you don't have as many friends around you to cover up your nudity. So because of that, people can kind of see what's going on a little bit more, and that might make you blush. All right, so if that's the case, that is the aldehyde. It is more exposed. These other nucleophiles can see it. It can see the partial positive dangling charge that's there, that's hanging out. And because of that, folks, that's just the way that it is. So now that you know there's a difference between the aldehyde and the ketone tendency to react, we need to take it another step further. We need to go in and talk about the ketones now. So at this point, you kind of understand the functional group of a ketone, at least I hope you do, and you know as good as well as I do that there could be simple little carbons over to the left and to the right-hand side. Or there could be a ketone that just has a simple little carbon to the left and more of a chain or something branched on the other side. Or we could have a ketone that could have some carbons on the left, and maybe on the other side we could end up with something like a ring structure. So as you can imagine, all of these scenarios do play a factor in the tendency of a ketone to react. And what we typically say is that alkyl groups stabilize the compound. The bigger these alkyl groups are, the more larger these alkyl groups are, the more stable that ketone is going to be. So if we are looking for reactions, that's the kind of the take-home message here. Aldehydes will react first because they are more exposed. They have this hydrogen. It has a different electronegativity than the carbon that it's attached to, and these are more prone to react and give us some compounds or some products from those reactions. In regards to the ketone, the same type of thing happens here. This is kind of going to react second. These are a little bit more stubborn because they have different groups that are attached to each side of the carbon other than a hydrogen, all right? And depending on those groups, the bulkier they are, the bigger they are, the more stable they become, and the less reactive that they are. So out of the three choices, as far as the ketones go down here in this example, this one would be the most reactive out of the ketone. This one would be the second reactive out of the ketone. And when we bring in big fat rings and these circular structures, that of course is the bulkiest of them all, and that will be the least prone to reactions in this scenario or in this scheme. All right, so it's all about how big these groups are on either side of the carbon. Now, if we have to go and squeeze the aldehyde and ketone into the lineup, folks, this is what we're going to see right here. All right, so this is a blend of type 1 and type 2 carbonyls. So if we look for where the aldehydes and ketones are going into, the aldehydes and ketones are going kind of smack dab in the center. So what beats out an aldehyde or a ketone? Well, the aldehydes and the ketones, the acyl halides, of course, are the most reactive. They have the ugliest functional group of them all right? And then we take a look at the acid anhydrides. The acid anhydrides will come next. Then the aldehyde, then the ketone, and then the remaining of the type 1 functional groups that we've talked about. The ester, the carboxylic acid, the amides, and the carboxylate ions, all right? So there is the lineup of the reactivity or prone to reactivity as far as type 1 and type 2 goes that are combined. Now, keep in mind, the nomenclature chart is for nomenclature only, right? So we've talked about the nomenclature rules, which one takes priority over the other, and so forth. That chart had nothing to do with reactivity. That chart had nothing to do with how prone they are to react. It was only about nomenclature, and you need to remember that, all right? Do not confuse the nomenclature chart with the reactivity chart, because they're often not the same. So here is a summary right here of all of the functional groups that we've talked about in type 1 and type 2, and where aldehydes and ketones fit into that picture. So acyl halides, as expected, are the most reactive. The acid anhydride would come in next, and remember, that is the group that looked like this. So this was a very good leaving group, a very ugly group that the molecule did not want, and that could easily leave and allow a nucleophile to come in and take its place. Then the aldehydes and ketones come next, and then after that would be the esters, the carboxylic acids, the amides, and the carboxylate ion. All right. Now, keep in mind, in type 1 reactions, we gave these reactions a name. We said that these were nucleophilic acyl substitution reactions. And the reason is because we had this group that had a leaving group on it, and a nucleophile came in, attacked the carbon, the oxygen shoved the electrons up, then it shoved the electrons back, and then carbon says, bye-bye, you're a leaving group, you're ugly, don't want anything to do with you. So this was the substitution part, and we said that type 1 carbonyls undergo that type of mechanism. In type 2, with aldehydes and ketones, we've not done an example yet, but in type 2, the narrative changes. We already know how it changes. We have a carbonyl. This carbonyl will have an incoming nucleophile. That incoming nucleophile is going to allow the carbon to shove the electrons up. Oxygen wants to shove them back in order to make this single bond. but carbon cannot get rid of a leaving group. Carbon's kind of stuck at this point. So we will have this negative oxygen that hangs out for a little bit. Well, this is not a substitution, is it? No, we're not substituting anything. We're adding onto the molecule instead. Top 1 carbonyls undergo substitution. A group comes in, replaces a group that is already there. In top 2, that narrative changes. In the top 2 reactions, the nucleophile comes in, attacks, attaches, and nothing gets replaced. The nucleophile just gets added on. So because of that, these are called nucleophilic addition reactions. So that is the new title or the classification that these reactions will undergo. Nucleophilic addition reactions. So in the aldehyde and in the ketone lectures and the reactions that you'll see upcoming, you will see that these are addition reactions. Nothing really pretty much is getting left behind. Nothing's getting kicked off of that carbon. We are simply adding onto that carbon. That double bond is breaking, and that double bond cannot reform. If it does reform, carbon's got to get rid of something. And that's called a substitution reaction, which means that these are top 1 carbonyls now and not top 2. All right, so just a little bit of summary about what we're getting ready to experience, the differences between the mechanisms, the differences between top 1 and top 2, and goodness gracious, we only have aldehydes and ketones in top 2, so what really is there going to be to it? You'll see in the upcoming videos.